quiz on Monday? Is it too easy? Oh, it's not too difficult, right? Okay, so we have actually scanned the optical form already, right? We are just in the middle of finalizing a few small things. Like as usual, there are students who circle their matriculation number incorrectly, right? So we need to try to find out who the particular student is. Right, okay, so the mark likely would come out by this week, right? We'll try to get it ready by this week, okay? If not, then latest will be next week. Right, so the mark list, we'll post it on Adventure, right? You'll let you know a bit later, okay? And actually, I also understand that for those of you who did the quiz in LT26, who did it in LT26? Some of you, 26. Is the light off for a couple of times? Do you know what's the reason why the light was turned off? Anyone? Sorry? Construction? No, not construction. Actually, we did a bit of investigation. It turned out that we find that, right, probably some of you already know, as you go out, some students actually find that their hand is a little bit itchy, so they just go and press this button here. This button actually is the power switch. So they thought it's a door release, so they go out, they press this button, and then suddenly the whole thing goes off. So it happened, I think, 2 or 3 times. Right, so next time, during the next CA, make sure you don't press this button, okay? Otherwise, it's going to happen again. Right? So anyway, 2 or 3 of you who press the button, you know who you are. All right, okay. All right, so right, so for those of you who come in late, let me just quickly recap in case we receive any email. Right, the mark will try to, the mark will try to release it by this week, but in the event we cannot due to some reason, then it will be next week, right? Okay, so before the quiz, actually we talked about this JPEG encoder. So we'll try to quickly go through some of the key ideas again, because if I just go directly into it, there may be a gap that you cannot quite follow. So let me just quickly refresh your memory again about what we have discussed about the JPEG encoder. So JPEG is a very popular image compression standard. By now you should know, right? It consists of a number of key steps. So let's try to quickly refresh what we have done, and then so that we can move on. Okay. Right, okay, so for JPEG, the first step is that given a particular image, right, it can either be in a RGB color space or it can be in YCV-CR color space. Sometimes you may want to convert the image into this color space is because our eyes are more sensitive to the luminance component than the chrominance color component. This is brightness, this is color. So if you convert into this component, this color model, sometimes you can perform some subsampling here. Right, this you will learn a little bit more when you talk about the video. Right, okay, so this is, and afterwards for each of the image you have 3 channels. What you're going to do is that you're going to take the image, you're going to partition it into 8 by 8 blocks. Right, so for this image you're going to partition it into 8 by 8 blocks. So each of the 8 by 8 block is showing as here. Oh, the battery is a bit flat already. Huh? Okay, and then for each of the 8 by 8 block, you are going to perform a process called DCT, discrete cosine transform. Okay, the reason why you may want to take this image and perform DCT is because the image in this particular original domain, right, you may not be able to compress it so readily. Once you have performed the DCT into the transform domain, the DCT coefficient contains some good property that you can exploit to perform the compression. Right? So that's the reason why you want to perform this compression here. So after you have, you want to perform this DCT transform here. So after you have transformed, you're going to get 8 by 8 DCT coefficient here. Sorry, the battery is flat already here. Right, so you're going to get an 8 by 8 DCT coefficient at this particular juncture here. So you're going to perform a process called quantization. This is the process last time, during the previous lecture, we have not discussed. So later on, we're going to discuss it. So we are going to take each of these 8 by 8 DCT coefficient, we are going to let it go through a process called quantization. And the outcome of this particular process is you are going to get 8 by 8 quantized DCT coefficient. Okay, 8 by 8 quantized DCT coefficient. And afterwards, you are going to go through a process known as a zig-zag scanning. We'll talk a bit more about it. Right, and then you have the DC and the AC coefficient. The first coefficient at this corner here is known as the DC coefficient. The rest of the 63 is known as the AC coefficient. So we are going to handle this DC coefficient and the AC coefficient separately. Right, so for the DC coefficient, we are going to use a technique called differential coding. For AC coefficients, we're going to use a technique called run length coding. Right, and then afterwards, these two, we're going to use a technique called Huffman coding. So this Huffman coding, later on, again, I'll talk a little bit more about it. So once you have done all these things, finally, you can pack all the information into the JPEG format, based on the syntax. Right, so this is the general overview, just to give you an idea again, in case you have forgotten, since it was last Thursday. Right, so this we have actually covered, so I'm just going to quickly go through it. So as I mentioned, the first thing that we do in JPEG compression is that given a particular image, we try to partition it into multiple 8 by 8 image blocks. And then for each of the 8 by 8 image block, you're going to pass it to do the DCT transform. Okay? So this is the idea. You partition it into an 8 by 8 image block. Right? For example, it may look something like this. And then each of them, you're going to pass it to the DCT to perform the transform. Right, so the DCT transform, early on, as I told you before, why do you want to do DCT transform? Anyone? Why do you want to do DCT transform for JPEG? The reason why you want to perform DCT transform is because data, after you perform the transform, it contains some good properties that can help you to perform the compression. So that's a high level understanding. So how exactly do you do this DCT transform? If you want, you can treat more like a black box, right? This black box that perform mathematical operation. So the mathematical operation is defined by the equations here. So you don't have to know about the detail. You just need to know, okay, so you have an 8 by 8 image block. You go into a mathematical operation called DCT transform, and then the output will be the DCT 8 by 8 DCT coefficient. Right. So this is one way you can look at it. You prefer to treat it as like a mathematical operation or black box. But for most of you, it will be good if you can also understand a little bit deeper about it. So this one we have shown you last time. Right. So the idea behind this DCT transform is essentially involve a center or a concept called change of basis function. Right. When you perform a DCT transform, you involve a change of basis function. So this basis function is like the Lego function that I've told you before. Right, so first, let me just quickly go through with you again, right, what I have explained when I tell you about the DCT transform from the perspective of a Lego basis function. So assuming that, first of all, let's focus on the 8 by 8, let's focus on a 4 by 4 image block like this. So a 4 by 4 image block like this. Right, okay. So first thing is that imagine that suppose if you have sets of Lego function. This Lego function is very simple. It's like what you play in primary school. The sets of Lego function consists of a collection of 16 pieces. Okay, let's consider first of all a 4 by 4 image block here for simplicity. Right, so the first Lego function that you have consists of 16 pieces, 16 different types of pieces. Right, so the first one looks something like this. It has a value 1 here and then 0 everywhere else. The second type of this function has a value 1 here and then 0 everywhere else. So by the same token, you can imagine the third and the fourth piece, how it looks like, correct? The fifth piece here actually has a value 1 here and then it's 0 everywhere else. Likewise, for the sixth piece, it's a value 1 here and then 0 everywhere else. So you can kind of imagine, right, you have 16 different types of Lego function in this collection set. This collection set is very trivial. There's a value 1 at the corresponding location and 0 everywhere else. So task number 1 that you have is that suppose you are given a particular 4x4 image block here. I only show a few pixel value because I don't want to show all the rest. It's too cumbersome. Suppose this 4 pixel value that you have is 2, 1, 3, 4. So the question is that given this particular Lego function set number 1, how many pieces of this is required to reconstruct this? How many pieces of this type of Lego function is required for you to reconstruct this? And so on and so forth. So in previous lecture, we mentioned very quickly that it's quite obvious if you think about it for one moment, right? Okay, the number of pieces that you need for this is 2, whereas this 2 value is nothing but the intensity or the gray level here, correct? And number of pieces for this, right, you can see it's 1. And why this is value 1? Because it's coming from here. So in short, what I'm trying to say is that for this Lego set number 1, the number of pieces that is required for you to reconstruct this particular image block is nothing but the coefficient values or the pixel values, correct? Right? So you can see now, one way of view of thinking about it is that given a 4x4 image block, actually behind the scene, it tells you that how many pieces of each of the Lego function is required to reconstruct it. So even though this thing is a little bit trivial, but that's how you can think about it. Given a particular 4x4 image block, essentially it tells you, or it can indicate to you, how many pieces of each of the Lego function for Lego set number 1 do you require to reconstruct the image block. So this is one very simple, intuitive way of interpreting the image. Another way, right, which is involving a change of basis function now, is that you imagine that you have this particular basis function now. So this basis function is more complicated. It's called the DCT basis function. Okay, so this DCT basis function, right, what we have, as I mentioned to you before, right, if the color is bright, that means its value is large. If the color is dark, that means its value is small. So if you look at this particular second set of Lego functions that you have, again, first thing you observe, there are 16 different types. Okay, 16 different types. The second thing is you notice that, all right, for example, for the first pieces that you have is flat value. That means you can kind of imagine, right, it's 4x4, the value is flat. Okay, and then this particular piece that you have, if you take a knife, you cut through it horizontally, this value is large, this value is small. So it's large and then small. Okay, and then this thing is large, small, and then this one is even faster. So one thing you observe is that as you travel through this particular axis horizontally, the pattern tends to become faster and faster. Initially, it's flat, there is no variation. And then the next piece change slowly. The next piece change even faster. The last one, fourth one, even faster here. Right, so you can imagine that moving down horizontally, you have the same pattern. Right, this means that moving in this direction is diagonally, it changes very fast as well. Right, so this is just trying to give you an overview, or at least some intuitive feeling about this DCT Lego function. Right, okay, so now the next thing is that, right, so when you have you have the same Lego same image block that you have as before. Now the task that you have to do is that the task that I give it to you is, given this particular image block, right, the question that I'm asking you is that how many pieces of this, 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 and each of them is required for you to reconstruct this particular image block. Okay, so that is the question. So how many pieces, this one is corresponding to this one. How many pieces of this is required is coefficient, I call it S00 here. How many pieces of this is required is coefficient, I call it S01 here. So the number of pieces that's required for each particular of this Lego function, this particular number of pieces is nothing but the DCT coefficient, right? So the number of pieces, the number of pieces that's required, the number of pieces that is required here, if you stack them based on this, if you stack them together, it's nothing but your DCT coefficient now. Right, so that's why it involves this, the DCT transform, you can see, right, is essentially looking at the same signal, but you look at it from a different basis function, right? So this is the new basis function here, right? It just means that how many pieces of this is required, right? So once you have some idea that when you're performing DCT, essentially what you have, okay, there's two ways you can think about it. One way is, given an image block, you can treat it purely like a black box or a mathematical process. You perform a DCT, you get an 8. For this example, if it's 4 by 4, you're going to get a 4 by 4 coefficient. Right? That's one way you can think about it. Another way, which is if you can have a deeper understanding, what it means is that given a particular 4 by 4 image block, when you perform DCT, essentially the question you're asking yourself is, how many pieces of each of these is required? Okay? And each of these, the number required is, you put together, is your DCT coefficient. Right, okay, so that is the overview. Right, however, for JPEG image, we know that for JPEG image, we partition the image into 8 by 8 image block. So earlier on, I showed you the example 4 by 4 is because it's a little bit easier for you to visualize. But in practice, right, for JPEG, you are going to use an 8 by 8 DCT basis function. So this Lego function is a little bit more complicated. But you do observe the same pattern, right, as you move it, for example, horizontally in this direction. Right, the frequency initially is flat, and then gradually it becomes faster and faster. Okay, horizontally. Likewise, vertically, as you move down, you can see the frequency become faster and faster. Right, so you may ask, right, okay, so now we have actually provide the interpretation on how do we calculate the DCT coefficient, either as a black box, which is a mathematical operation, or the number of pieces that you need, for each of these to reconstruct an 8 by 8 image block. All right, so the natural question is that why do you want to, early on we say that the reason why we want to perform DCT is because this particular 8 by 8 image block, after you perform a DCT, the DCT coefficient possess some good properties that make it easier to perform the compression. But exactly what are these good properties? Okay, so in order to answer that particular question, you just have to, right, let me just refer back to this particular slide here. Right, okay, so if you imagine that given a particular 4 by, let me see, given a particular natural image block, for example, given a 4 by 4 image block from a natural scene, right, from a natural images, right, do you think you need more of these types of pieces of Lego function, this type of Lego function to reconstruct it, or do you need more of these types of Lego function to reconstruct it? You need more of this type of Lego function here, or more of this? This is A, this is B. A, because I asked the question before, right? The answer is A. But now, why is it that you need more of this type rather than more of this type? The reason is because for natural image, your pixel value tends to change slowly. If your pixel value tends to change slowly, you just use your imagination a little bit, you can see quite clearly, because the pixel value tends to change slowly, you need these types of pieces where the change is more gradual, right, rather than these types of pieces that change more faster. But what's the meaning of that? If you need more of these types of Lego function, then more of this type of Lego function, what does it mean? It means that your DCT coefficients here near this region will be larger than near this region, correct? So what it means is now, actually the energy, okay, because the value or the coefficients near this region is larger than near this region, that means the energy has been packed into a small number of coefficients already, okay? And this particular thing is called energy compaction. That's why if you always hear DCT transform, you always hear of this term called energy compaction. Right, okay, so I think I'll give you a pretty thorough recap and also further explanation. So the next few slides is just trying to reinforce your understanding. Right, so earlier on, as I've told you, when you have an 8 by 8 image block, when you perform a DCT transform, you'll get an 8 by 8 DCT coefficients here. Right, so in terms of terminology, the first term is known as the DC coefficient. The rest of the 63 is known as the AC coefficient. So you can simply treat this particular process mapping from image block to this DCT coefficient as a mathematical mapping or black box if you want. But for deeper understanding, right, you should understand that this is essentially, when you perform DCT, it involves a change of basis. The change of basis means that, right, how many pieces of this is required, you write down its number here. How many pieces of this is required for you to reconstruct this, you write down the number here. So essentially, a DCT transform is trying to find out how many pieces of this basis function is required for you to reconstruct this image block. And the coefficient, you just write it down here. So by now, you should see that the values near this region should be very large, and the values near this region should be very small. Correct? Okay? And whereas for the pixel in the original domain, you have no way of telling, because each pixel, the value can be anything at all. So in its domain, you do not know which pixel is large or small. You have totally no clue. But once you are transformed into the transform domain, what you can be sure is that, right, for most of the images, values near here will be large. Values near here will be small. Okay? So to further consolidate that understanding, I'll give you an example. So you can see this is an example that you have here. So this is an 8 by 8 image block here. So how do you interpret this image block? If the value is bright, if the color is bright, that means its value is large. If the color is dark, that means its value is small. That's usually how we interpret. So you can do cross-check this with a sample, for example, the gray level. For example, bright here means that the value is larger here, 50. Okay, dark here means the value is small. You can see about -6, 1 here. Right, okay, so this is the pixel in the original domain. Okay, in the original domain. After you perform the DCT transform, you can see this is the DCT coefficients here. So when you check this DCT coefficients here, one thing you notice is that this range here, the pixel value tends to be brighter than here. This tends to be darker. So what it means is that you can see the DCT coefficient near these regions here are larger as compared to this region here. There are lots of zero already. So this is one example just to demonstrate to you. Right, okay, so earlier on, I asked you to use your imagination a little bit, dark means small value, bright means large value. So you can also see that, right, this particular graph here actually, instead of asking you to visualize, actually provide a 3D view, so as to help you to understand. So what it means is that when you calculate a DCT coefficient here, what it means is that how many pieces of this type is required for you to reconstruct an 8 by 8 image block. Okay, the number of pieces is required is the DCT coefficient for this. How many pieces of this type of Lego function is required? You can see this Lego function, just like I asked you to imagine you use a knife to cut through, the value is large to small, correct? So now I just should give you a 3D view. So the number of this type of Lego function is required, right, is a DCT coefficient for this. So by the same token, you can imagine, right? So again, this is just to give you a better overview, right? Because now you have a 3D view. I think most of you now can be quite clear, right? Okay, so next, right? Earlier on, actually, I already explained this. Why do you want to perform DCT transform? The reason is because the data, once you transform into the transform domain, this transform data will have some good property that you can compress it more easily. So that's the reason, because the compressed data is more suitable for compression, right? Okay, and then this particular transformation uses energy compaction. By now you know what's the meaning of energy compaction, because most of the coefficients near these regions are very large. Most of the near these regions are very small. That means the energy now is packed to a small number of coefficients here. In the original domain, you have totally no idea which pixel is large or small. So the energy is evenly spread out or evenly likely. But after the transform, you know this part is going to be large and this part is going to be small. So this particular observation is known as the energy compaction. And on top of that, it also mentioned that this transformation can perform what we call a redundancy reduction. It says that it reduces the correlation between the coefficients, also known as the redundancy reduction. So anyone can guess what's the meaning of that? So for DCT transform, actually there's two good properties. The most popular one, usually we say all the time, is energy compaction. The second one, actually, it can also achieve this decorrelation, also known as redundancy reduction. Just based on the sentence, reduce the correlation between coefficients. Can anyone guess what it's trying to say? If I give you this particular figure, right? What's the meaning that DCT transform? It can reduce the redundancy. It can reduce the correlation between the data. What it means is that, anyone want to try? Right. Okay. Actually, this particular statement refers to this. If you consider a particular image, for most of the natural image, the pixel value between one location and the next location, they tend to be very similar. When there's very similar, that means there's lots of what we call redundancy, or in other words, there's lots of there's a strong correlation, right? There's lots of redundant information because I don't actually really need to know what this pixel is. By looking at its neighbor, I more or less can tell what this pixel is because the pixel values change so slowly. So if that's the case, that means they actually contain lots of redundant information in this data here, right? So that's the observation in the original spatial domain, if just talking about the gray level. As opposed to this, if you look at this particular, once you perform the DCT transform into this transform domain, actually this pixel value and this pixel value, we have no idea how much they are, right? They are maybe totally different. So if they are totally different, that means there's not a lot of redundant information there. You can't really tell. You have removed lots of redundant information already. So actually that particular statement just simply states that, okay, when it reduces the data redundancy, means that, okay, in the transform domain, this value and this value, they are not related by too much at all. They are not related, right? If they are not related, that means you remove lots of the redundant information already, which is good, right? Because if there are lots of redundant information, that means you can further do better to further remove it, right? Okay, so this is the meaning of this. You reduce the correlation, okay, between the coefficients. Right, okay, so earlier on, as I told you before, for this DCT transform, right, what you have is you have an 8x8 image block. After you perform a DCT transform, you're going to get an 8x8 DCT coefficient. This one, the first coefficient is known as the DC coefficient. The rest are going to be known as the AC coefficient. Right, and then for this AC coefficients here, you can see as you move it horizontally, we say you have an increasing spatial horizontal frequency. All right, if you move it down, we say you have an increasing vertical spatial frequency. Right, what's the meaning of increasing horizontal spatial frequency and increasing vertical spatial frequency? In order to understand the statement, you just need to look at this basis function here. You can see as you move it horizontally, you can see clearly the coefficient that is corresponding to this basis function is becoming faster and faster. Right? That's why you have an increasing horizontal frequency. This one you have increasing vertical frequency. Right, okay, so what we have studied so far is simply like this. Given the image, step 1 is that we partition it into 8x8 image block. And then for each of the 8x8 image block, we are going to let it go through a DCT transform to get the 8x8 DCT coefficient. Right, so the next step is that you need to perform a process called quantization. So in order to understand how this quantization works, let's look at the table first, and then we'll come back to this particular slide. So the quantization process is very simple. So what you have is that, suppose this is the DCT coefficient that you obtain, right, after you perform the transformation. In order to perform this quantization, what you need is a quantization table. Right? What you need is a quantization table. And then what you do is that during the quantization is you take each of the coefficient here, all right, you divide by this step size, and you round it to the nearest value. For example, 120 divided by 10, you round it to the nearest value, clearly is 12. For example, 40, if you divide by its corresponding value, 15, you round it to the nearest value, you see is 3. Okay, so this is the process you perform the quantization. Right, so for this quantization table, you do notice something. I want you to tell me, what do you observe from this quantization table? What do you observe from this particular table here? Okay, but before that, maybe let me just tell you, why do you want to perform quantization? Why do you want to perform quantization when you're performing JPEG compression? The reason is because for this particular DCT coefficients here, the values are actually continuous values. It can be any values, it's a continuous value. But after you perform the quantization, right, the values that you have is a finite value, right? I think most of you who study a bit of physics before, you know the idea of quantization, right? From a continuous value, after you perform quantization, you have a finite set of value only. Okay, so that's the purpose of performing quantization. But if you look at this particular quantization table here, you'll notice that there's a certain trend or pattern. What is the pattern or trend that you observe? What do you notice? What do you notice? I think it's not difficult for you to notice the pattern. What is the pattern you observe? First, as you move from this region to either you move horizontally, you move vertically, or you move diagonally, you can see that the step size becoming larger and larger, correct? Okay, that's the general observation. Now, the second question is, why is it so? Why do you use this kind of quantization table? What is the rationale behind it? Why do you want to do this? Anyone? Why do you want to do this? The reason why you want to do this, actually, there's twofold. There's two reasons why you want to do this. The first thing is that, right, if you notice that early on, we have told you before that after you perform DCT transformer, the coefficient near these regions are very large. Okay? Right, if the coefficient near these regions are very large and the coefficient near these regions are very small, that means you should preserve more resources or number of bits to encode coefficients near this region, correct? Because most informations are lying here, so of course you should dedicate more bits to encode this region. If you want to dedicate more resources to this, that means your quantization step size here must be smaller. Because smaller step size means you lose less error, correct? Larger step size means that you lose more error, correct? So, but this part, because its value is so small, so you divide by a large number, it's okay. You only lose a little bit of information, because most of the information is lying over here. So, because most information is lying over here, we should make the step size here smaller, so that we can preserve more information and lose less information. That's number one. Number two is because our eye, human eye, are more sensitive to low frequency or high frequency component. Low frequency component, huh? So we know that human eyes are more sensitive to low frequency component than high frequency component. So what it means is that, right, if you ask yourself, for this DCT coefficient here, this part has low frequency component or this part has low frequency component. Which part? Which part? A or B? Who thinks it's A? A? A few hands are very few. Who thinks it's B? Okay, right. I'm not sure whether you are the same person who raised your hand twice or whether it's your friend. Right, okay. But anyway, the answer is that actually the coefficient in this region is the one that corresponds to low frequency component. The coefficient near this is the high frequency component. Why? You may ask why. The answer to that question is, again, very simple. You just look at this particular basis function. The coefficients near this region means that it corresponds to this kind of pattern. Of course, this kind of pattern changes very slowly, right? So that's why you have low frequency coefficients here, as opposed to here. Here you have high frequency component here. So what it means, therefore, now is that because our eyes are sensitive to this low frequency component than high frequency component, therefore we have better make sure that there's little distortion or little error is introduced here, because our eyes is sensitive to any errors near this region as compared to here. And because you want to have less error near this region. Of course, obviously, the natural choice is you want to keep the step size here small, so that the amount of information lost here is little. Okay, so I think that is pretty much the main point that I'm trying to say. So pretty much the point that is given here is what I've just told you. Humans are more sensitive to the low AC coefficient, right? So that the high frequency information, you can either discard it or you can de-emphasize that. Right. Another thing is that you notice, as in any quantization, information will be lost. Yeah. Because you divide the number, you round to the nearest integer. Definitely, some information will be lost. Right. Okay. So the quantization is performed by taking the DCT coefficient, divide by the step size, round to the nearest number, as I've just explained. Right. One more thing it mentioned is that the value in the table is a compromise between the compression and the information loss. What it means is that this particular table here, if the value, if I want, I can increase the value for all the step size. But what is the price you have to pay? If you increase the value, in each of these particular step size here, what will happen is that your compression is going to be more effective. You are going to compress it into a smaller number of bits. But what is the price you have to pay? What is the price you have to pay? Quality loss. You lose more information. So it's a trade-off between those two factors. Right, okay. So once you have done this, the next step, so far we have an image partitioned into 8 by 8 image block. Each of the blocks perform DCT transform. The DCT coefficient, we perform quantization to get a quantized coefficient. So we are come near to the end of this already, but so bear with me. Right, the next step that we have to do is that we have to do something known as an entropy encoding. The idea of entropy encoding is something like this. Right, okay. When you try to encode something, patterns that occur more often, you can assign shorter number of code work to represent them. Right, patterns that occur less often, you can afford to assign a longer number of bits to represent them. Do you get what I'm trying to say? It's, for example, in your normal English, you have alphabets A, B, C, D, all the way up to Z, right? So one way you can do it is that you can say, okay, no, I don't really care. Each of the alphabets that I have, I always transmit, for example, using, say, 4 bits. Okay, every time I just send 4 bits over. Right, that's one way you can do it. Right, but is this a good way? Is it a clever way of doing it? Is it a clever way of doing it? Let me see. 4 bits, actually you need at least 5 bits because there's 26 alphabets. That means you need at least 5 bits. Right. Suppose one way, scheme number 1 is very simple. Right. A, B, C, D, E, I don't care. Every time I see A, I just transmit 5 bits that correspond to A. Every time I see B, I transmit another 5-bit pattern and so on and so forth. Alright, so this is one way you can do it, but do you think this is a clever way of doing it? Yes or no? No. Why? Why not? Sorry? Too many bits to represent? No, not really, because you have 26 symbols, right? You at least need 5 bits. 4 bits only give you 16 patterns, so you at least need 5 bits. Right? Anyone? Okay, the reason why this is not a very clever way of doing it is because if you look at the statistics of English alphabets, some alphabets occur more often than the others. Am I right? Correct? What are the alphabets that occur most often in English? Sorry? Okay, actually, sorry, come again. Vowel. Actually, to be frank, I do not know the answer as well. My initial guess is something like T or something, but probably you know better than me. Is it T? E. Maybe it's E. Right, okay. So you can see quite clearly, right, some alphabets like vowel or S or T, they occur more often, right? As compared to some other alphabets like what? Z or Q, that occur very less, not so often. So a smarter way of doing that is that for those alphabets that occur more often, you translate it using shorter code words, right? Use 2 bits or 3 bits to transmit them. But for those patterns that occur less often, like Q and Z, we use the longer bit, say 7 bit, no, 6 bits to transmit it. Okay, the reason why you do that, you can think about it is overall, if you take all these factors into consideration, on average for any typical English message, in total you're going to require less number of bits if you use the second approach. Am I right? Correct? So therefore, this is the essence of entropy encoding. Entropy encoding essentially just says that patterns that occur more often, I use a shorter code word to represent it. Patterns that occur less often, I use a longer code word to represent it. It's simply that. Okay? So this is the idea of entropy encoding. And there's many ways you can do entropy encoding. Among them, one of the more popular ones is called Huffman coding. So Huffman coding is actually based on the idea I told you before. More frequent pattern, you use a shorter code word to represent it, and vice versa. Okay? Less frequent pattern, you use a longer code word. Right? Okay, so this is the idea of entropy encoding. Right? And on top of that, this entropy encoding also involves the idea called zig-zag scanning and Huffman coding. Huffman coding I've explained. There's also one more step called zig-zag scanning. So zig-zag scanning, the idea of zig-zag scanning is like this, right? So earlier on, as I've told you before, assuming that this is your quantized DCT coefficients already. All right, so this quantized DCT coefficient, you have 8 by 8 coefficients here. So typically what you'll do is that you'll convert this 8 by 8 coefficient into a 64-dimensional vector. Right, so how do you do the conversion? You scan the coefficient in this particular manner called zig-zag scanning. Right, so if you follow this particular order of writing out the coefficient, you'll be able to convert this 2-dimensional array into a 64-dimensional vector. Now, the question is, why do you scan the data in that particular order? Why? Why do you scan the data in the particular order? The reason is because, right, okay, because we are running out of time, so I have to tell you the answer. Right, so if you look at this particular example here, so after you perform the quantization, you can see that you have some coefficient here, but the rest of them, you have lots of zero. Okay, you have lots of zeros. So this is a low frequency coefficient, this is a high frequency coefficient. So what we are going to do is that if we scan it in this manner, we will manage to lump all this zero together. We will lump it together. When you lump this zero together, it will be easier for you to compress it later. So the reason why you scan it is like you can link all these low frequency coefficients together and you separate them from the high frequency coefficient. Okay? Right? Because you know that for this high frequency coefficient after quantization, there's lots of zero inside that you don't have to worry too much. So that's the idea of zig-zag scanning. Right? So once you have that, once everything is ready, the next thing is that, right, you will be using the entropy coding to, the Huffman coding to encode it. The detail you don't have to know too much. But the final step that you need to do is you need to do a frame building. Right? Once you have all those information, you still need to pack it based on the proper syntax in JPEG before you transmit it or before you save it into a local drive. So this particular process of packing everything properly is known as a frame building. Okay? So the frame building is just make sure that you put all the information in a proper structure, okay, and then store it. Right, okay, so I think with that, we pretty much finished the first part of this particular lecture. So for my part, there's still two more things. One is the camcorder. The next one is the home entertainment system. Right? Okay, so I'll see you tomorrow.